Idaho has been rocked by the strongest earthquake in nearly 40 years. Preliminary magnitude 6.5 earthquake rattled Idaho on Tuesday, with shaking felt across the region, including Washington State, Utah, Nevada, and Canada. Perhaps most interestingly is that the earthquake was so strong that the eruptions of Old Faithful in Yellowstone National Park were noticeably longer. According to a report 2 weeks ago by National Geographic, the caldera has been experiencing a type of pulsing, but new research does not indicate that the supervolcano that created the Yellowstone caldera is more likely to erupt now. The last time it happened was 640,000 years ago.
Will be the mother of all ash clouds, an aerial mountain of deadly particles and debris. Yellowstone National Park is the site of a recurring supervolcano. An eruption so large that if it happens again, it would destroy nearly everything within 60 miles. But what would happen next as a mountain of ash begins to spread and then fall? The Yellowstone supereruption could throw ash 15 miles into the atmosphere. The fallout could cover half the United States.
Recent news coverage has suggested the Yellowstone volcano may be much sooner to eruption than previously thought. The Yellowstone caldera spreads beneath the states of Wyoming, Montana, and Idaho, and gets its nickname as a supervolcano due to its ability to inflict devastation. On a global level, it is constantly monitored by the United States Geological Survey for signs of a supereruption, something that has only happened 3 times in history: 2.1 million years ago, 1.3 million years ago, and 640,000 years ago, leaving some to claim a massive eruption is overdue. Until 2017, geologists thought it would take centuries for the supervolcano to undergo a critical change before an eruption. But after analyzing minerals and fossilized ash from a recent eruption, researchers at Arizona State University found the supervolcano last awoke after 2 influxes of fresh magma flowed into the reservoir below the caldera. National Geographic has covered the story, stating that a chunk of Yellowstone the size of Chicago has been pulsing, and wondered why. Just to be clear, the new research does not indicate that the supervolcano that created Yellowstone's caldera, which last erupted 640,000 years ago, is any more likely to erupt now. Instead, these geologic movements may help explain why the park's Steamboat Geyser, the world's tallest active geyser, has been erupting at record-breaking pace since March 2018. Researchers also speculate that the changes below Norris may mean a slightly increased chance of hydrothermal explosions taking place in the basin. Let's look at the USGS to answer the question of whether earthquakes can trigger volcanic eruptions. Sometimes, yes. A few large regional earthquakes greater than magnitude 6 are considered to be related to a subsequent eruption or to some type of unrest at a nearby volcano. However, volcanoes can only be triggered into eruption by nearby tectonic earthquakes if they are already poised to erupt. This requires 2 conditions to be met. 1, enough eruptible magma within the volcanic system. 2, significant pressure within the magma storage region. If these conditions exist, it's possible that large tectonic earthquakes might cause dissolved gases to come out of the magma, like a shaken soda bottle, increasing the pressure, possibly leading to an eruption. Now we're going to do a case study on the Yellowstone caldera. First, we'll examine the known attributes of the Yellowstone caldera, then estimate a probability of a future eruption. Finally, we will explore several options for managing this risk. The Yellowstone caldera is a volcanic caldera and supervolcano in the Yellowstone National Park in the northwest corner of Wyoming. It is said to have been formed over successive eruptions taking place within the last 2.1 million years. These eruptions occurred 2.1, 1.3, and 0.63 million years ago, with ejecta volumes of 600, 67, and 240 cubic miles, respectively. It's pretty natural that people might be asking themselves, what are the chances that this thing is going to blow up? Interestingly, we've seen some research come out lately that shows people are looking at different models for how the magma moves within the Earth. So this is important because when I was going to school, basically what they told us is that we have tectonic plates at the surface and then sort of a harder, crunchier region before finally getting to a more molten region closer to the center. But it looks like the observations that have been compiled, there's a significantly more movement going on than people originally thought. They've compiled the first global set of observations of movement in the Earth's mantle, the 3,000-kilometer thick layer of hot silicate rocks between the crust and the core. And I found that it looks very different to predictions made by geologists over the past 30 years. The team from the University of Cambridge used more than 2,000 measurements taken from the world's oceans in order to peer beneath the Earth's crust and observe the chaotic nature of mantle flow, which forces the surface above it up and down, sort of like breathing, because this is all oscillating waveforms, right? So they have a period, they have amplitude, they go up and down. These movements have huge influence on the way the Earth looks today. Circulation causes formation of mountains, volcanism, and other seismic activity in locations that lie in the middle of tectonic plates, such as Hawaii and parts of the United States. Next, let's have a look at the geography. The Caldera is landlocked. It's about 886 miles from Portland. This location is dangerous because magma pressure is perpetually building under the North American landmass with no clear exit strategy. To get an idea of the approximate size of an eruption, if the smallest volume that's come out so far, which is the second eruption, happened again, it could cover a circle with a radius of 4.6 miles and with a wall of magma 1 mile tall. Alternatively, the same volume could cover a circle with a radius of 335.6 miles with a wall of magma 1 foot tall. For a reference point, the caldera is 376 miles from Salt Lake City, Utah. In order to estimate the time at which the Yellowstone caldera is likely to erupt again, we estimate upper and lower bounds by analyzing the known time intervals between previous eruptions. Note that the time interval between the first and second eruptions is longer than the time interval between the second and third eruptions. So let's assume that the same pattern happens again. There's a time compression factor equal to the ratio between the original time between eruptions and the next time between eruptions. It gives us a factor of 0.8375. If we use that as our estimate for the next eruption, we expect that this should have happened about 70,000 years ago. A high estimate would give us an expected date of eruption about 40,000 years into the future if we assume the same amount of time will pass between the last and the next one, then the one before that, and the last one. Let's keep looking at the timeline analysis. If we estimate the time compression factor, oh, sorry, I've already said this part. So this is a diagram of the previous eruptions. So we've got the size and the approximate location. So that they were pretty big when they erupted. So it's expected, if it erupts again, to be a similar pattern to what we've already seen. It thus follows that a management strategy for the Yellowstone caldera is worth undertaking. An evacuation plan for the region 1,000 miles around the caldera should be made and widely disseminated. Early warning diagnostic techniques should continue to be developed. More research should be committed to correctly modeling magma currents. Our advanced technology may indeed allow for an alternative and more invasive approach to mitigating this risk. We'll next explore 3 possible approaches to magma diversion, as well as their associated risks. So what we're going to do is look for a way to divert the course of this magma so that it doesn't end up covering a considerable chunk of the North American landmass with a volcanic eruption. So where do we go looking? What happens if we go to the Pacific Ocean? Notice there's an anomalously high temperature region in the ocean. It's been nicknamed the Blob. There's also an underwater volcano in this region called the Axial Seamount. Thus, the anomalously high blob temperature is likely caused by the magma being more proximal to the surface in the Axial Seamount region. What if we could divert the path of magma away from the Yellowstone caldera by triggering the Axial Seamount to erupt? A possible benefit of such a course of action could be. Next, we're going to examine 3 possible ways we can maybe trigger the axial mount to erupt. Idea 1, drilling. We may be able to repurpose oil drilling technology to drill into the seafloor. If a deep enough hole can be dug, this will forge a path of lesser resistance that magma can be drawn through. Idea number 2, bombing. Many powerful bombs have been manufactured. These could be repurposed and deployed to strategic locations on the ocean floor. Such locations should be selected to have maximal proximity to the epicenter of the axial seamount and maximal average seismic activity. So we want to target where there's already motion going on, as well as we want to give it a proximity to where this thing would erupt if it were to erupt naturally. These locations will serve as drop points for bombs, which will be detonated simultaneously. Simultaneous deployment will maximize probability of operational success because the combined force of all the bombs volcano. Idea 2.5, a combination of ideas 1 and 2. It may be possible to combine both drilling and bombing technology. Drilling beneath the ocean surface, the magma, and probability of operational success. Boom! How do you like that for an idea? An even more interesting idea might be to use sonar tech. Did you know that every substance has at least one natural frequency? This is because matter is foundationally wave-like. These frequencies are well substantiated through the phenomenon of matter waves. When a material is subject to particular frequencies, which are determined by their natural frequencies, the material will vibrate at above unity waveform amplitude. And that's what we can see so clearly in this glass picture. The energy and the vibrations is less than the energy of breaking the glass, is able to overcome its internal cohesion much more easily when made to vibrate near its natural frequency in a specific way. Such techniques derive from the ancient Vedic science of sonar tech. For a brittle material, like the ocean floor, sonar tech can result in shattering. So what we would do is construct something to send a targeted vibration in the direction of a weak point, and it would hopefully cause it to vibrate at the correct frequency that would allow for this above unity vibrational amplitude that could shatter the ground and allow for the magma to escape. An interesting idea because this is actually how places like Hawaii were formed. This is actually how possibly all land mass has been formed. While there are risks associated with such a course of action, such as the accidental triggering of nearby seismic activity, i.e. Los Angeles, the risk of not taking any action leaves many people's lives in danger. In fact, the risk of not acting may exceed the risk of taking action early on. An additional benefit could be the creation of new landmass in the Pacific Ocean, and people could go live there. Indeed, this is how Hawaii was formed. So it's important to understand what's going on, understand the risks, and look at the possibility of what are the options. I mean, if we have no option of diverting a magma, we just have to deal with the fact that we have to expect that this is going to go off at some point. How are we going to mitigate that risk? I don't think we've taken enough steps in that direction. And I think at least investigating these other avenues could be very profitable in the long term and lead to greater health and safety. Thanks so much for tuning in. We'll talk to you again real soon.